We live in an age where machines are becoming artists, composers, and writers. But the fundamental question remains how exactly a machine learns the underlying rules of creation, the hidden grammar of reality itself. Previously, we've encountered impressive techniques. We've seen generative adversarial networks, or GANs, that literally dream images from fields of pure noise, creating photorealistic outputs by having two networks compete against each other. We've also explored variational autoencoders, or VAEs, which specialize in compressing complex reality into a neat, hidden code, allowing us to traverse the latent space of concepts. These models often rely on complex sampling or approximation methods. They guess based on the probability distribution they have learned. Today, however, we shift our focus to a new, different class of operative in the world of generative AI. These models do not guess or approximate the answer. They deduce it, step by meticulous step, ensuring that every piece of the generated output is a high-fidelity consequence of what came immediately before it. This dedication to sequential precision defines the autoregressive models, and their story is one of meticulous order and chilling coherence. The subject of our investigation today, and the prime suspect in the case of synthetic creation, is the autoregressive model. Its modus operandi is strikingly simple and fundamentally brutal. To predict the future, it looks only to the past. It progresses one step at a time, without exception, explicitly modeling the joint probability of the entire sequence of data. This means that if we are generating a sentence, the fifth word is predicted based only on the four words that preceded it. What distinguishes autoregressive models from their generative cousins is their methodology. Unlike GANs or VAEs, they do not rely on a complex, hidden latent variable that summarizes the entire scene. Instead, they meticulously build reality piece by piece. Each new element, whether a word or a pixel, is deeply conditioned on every single element that was generated before it in the sequence. This sequential dependence ensures high local coherence. The investigation into this methodology will focus on two key operatives who specialize in this type of deduction. Case file 1 is the Ghostwriter, typically implemented using long short-term memory networks or LSTMs, which specialize in sequential text data. Case file 2 is the digital forger, exemplified by the PixelCNN, which applies this sequential logic to the complex world of image construction. Our first deep dive takes us into case file 1, the Ghostwriter. The subject here is the long short-term memory network, better known as LSTM, which is a specialized type of recurrent neural network, or RNN. Traditional RNNs struggled with long-term memory, often forgetting the beginning of a story by the time they reach the end. The LSTM, however, was designed to solve this exact problem, making it the perfect ghostwriter, able to maintain coherent narratives over vast sequences. To understand its operation, imagine a secure, elaborate facility responsible for monitoring an unfolding story. This facility holds, say, 256 specialized informants, which we call the units or cells. Collectively, these informants are responsible for maintaining the entire, complete memory of the story so far. Every new piece of intelligence, such as a new word, is fed into the facility. Each individual informant then updates its internal assessment based on this new input, and also based on the chatter and reports from the other informants. Through this sophisticated internal mechanism, the entire group collectively decides on the most logical and likely next word in the sequence, which is then immediately fed back into the system as new intelligence, continuing the cycle of deduction and generation. This internal flow of information, guarded by a series of precise protocols, is exactly how the ghostwriter maintains long-range coherence in sequential text. To truly understand the ghostwriter, we must venture inside the cell, where the interrogation protocols manage the flow of information. An LSTM cell maintains two critical logs that allow it to manage both short-term relevance and long-term history. First, we have the cell state, denoted as C sub t, which represents the complete, unfiltered internal memory. This is the long-term record, stretching back across the entire sequence. Second, there is the hidden state, H sub t, which is the official, condensed report. This is the working memory that is immediately sent to the next operative in the chain to influence its decision-making. These two logs are regulated by three specialized gates, each acting as a highly specific filter. The first is the forget protocol. This gate analyzes the new intelligence x sub t and the last official report h sub t-1 to determine which parts of the old long-term record, c sub t-1, are no longer relevant to the ongoing narrative and must be discarded or faded out. The second is the input protocol. This gate works to determine what specific new information is critical and needs to be added to the long-term record, and in what specific capacity or magnitude it should be included. Finally, we have the output protocol. After the long-term memory has been updated, this gate determines what exact portion of the newly updated internal record, c sub t, is most relevant for the next immediate action. This critical decision forms the new official report, h sub t, which is passed down the line, ensuring that only the most pertinent information influences the very next generated step. Before the Ghostwriter can begin its work, the raw, discrete text must be converted into a form that the machine can process mathematically. This process of preparing the intel is divided into three crucial stages, moving from text to numerical vectors. The first stage is tokenization. Raw text, such as the CatSat, is fractured into its most fundamental units, or tokens. This involves handling punctuation, isolating words, and often converting everything to lowercase for consistency. A finite vocabulary, perhaps comprising the 10,000 most common tokens, is established. Any word falling outside this accepted vocabulary is generically categorized as an unknown token, or UNK. Once tokenized, the sequence moves to vectorization. In this second step, every unique token in the established vocabulary is assigned a corresponding unique integer identifier, or ID. This creates a purely numerical sequence that the model can now start to work with. However, a single integer ID still doesn't capture the subtle relational meaning that is so critical to language. This leads us to the final and most powerful step, embedding. Here, each integer ID is mapped to a high-dimensional vector, commonly 100 or more dimensions. This is far more than just a simple lookup table. The model learns these vectors during training, positioning words with similar semantic meanings closer together in the high-dimensional vector space. For example, the vector for the word king will be mathematically closer to queen than to truck. This is precisely how the network learns to understand and manage the underlying context of the language it is generating. The proof of the Ghostwriter's capability lies in the evidence it produces, the generated transcripts. This model, trained on source data like the Cornell movie dialogues corpus, demonstrates an uncanny ability to generate text that maintains both tone and context. Consider the prompt. He walked into the bar, the smell of cheap whiskey and desperation in the air. He said. The response generated by the model is highly dependent on a crucial hyperparameter known as temperature. The temperature parameter effectively controls the randomness of the prediction. When we set the temperature to a higher value, such as 1, we get higher variance and a more creative output. The response is unexpected and evocative. Give me a reason not to burn this place to the ground. Conversely, when we set the temperature to a lower value, such as 0.2, the variance drops significantly, resulting in a more predictable, safer prediction. The generated dialogue, "I'm looking for a man," is standard and expected for the context. Low temperature forces the model to stick strictly to the most probable path, whereas high temperature allows for more statistically improbable, creative, and sometimes nonsensical detours. In both cases, note the model's sophisticated grasp of the setting, the necessary dialogue structure, and the overall context of a film noir scene, proving its mastery of sequential deduction. While the basic LSTM cell is powerful, its true capabilities are unlocked through advanced architectural tactics used to deepen its efficacy. The first tactic involves stacked networks, which we call deepening the conspiracy. Instead of just one layer of LSTMs processing the sequence, the hidden states output from the first LSTM layer become the input for a second, and potentially a third LSTM layer stacked directly above it. This vertical stacking allows the network to learn progressively more complex features at multiple levels of abstraction, similar to how deeper convolutional networks learn edges, then shapes, then objects. Second, we have the gated recurrent units, or GRUs, which are the streamlined operative of the recurrent world. The GRU is a variation on the LSTM, but features a simpler, more compact architecture. Crucially, it merges the distinct cell state and hidden state into a single vector and uses fewer gates, typically only 2. This efficiency often makes GRUs faster to train and deploy, while being just as effective as LSTMs for a great many sequential tasks. Finally, and most powerfully, we have the bidirectional cells, which offer the ability to see the whole picture. Standard LSTMs are inherently limited. They are prophets who only know the past. A bidirectional architecture overcomes this by running 2 separate recurrent layers simultaneously. One layer processes the sequence forwards in time, while the other processes the exact same sequence backwards. The resulting hidden states from both directions are then concatenated. This provides every single prediction point with the full context of what came immediately before it, and, uniquely, what comes immediately after it, significantly improving context awareness. We now turn our attention to case file 2, where the autoregressive principle leaves the domain of sequential text and enters the domain of spatial data. Our new pattern is the digital forger, the PixelCNN. The crime this subject specializes in is forging novel images with such uncanny stylistic coherence that they are indistinguishable from the source material. However, this shift presents a core architectural problem. Text and time series data are inherently one-dimensional sequences. Images, on the other hand, are 2-dimensional spatial grids. If we want to maintain the rule of autoregression, how can a sequential model operate on a static canvas where all pixels exist simultaneously? The solution is to impose an artificial, yet strict, sequential order. The forger achieves this by scanning the canvas pixel by meticulously defined pixel. The order is fixed, left to right, and then top to bottom, like reading a book. By treating the 2-dimensional grid as a strict one-dimensional sequence, the model can adhere to the foundational autoregressive rule. A prediction can only be conditioned on the pixels that came before it in the defined scan order. This ingenious solution allows the sequential logic of LSTMs to be adapted to the complex spatial task of image generation, enabling high-fidelity output. The critical tool that enables the digital forger to maintain autoregressive integrity in 2 dimensions is called the blinder, formerly known as the masked convolution. Standard convolutional layers, which are the backbone of most image processing, inherently see all neighboring pixels simultaneously when applying their filter. This standard process immediately violates the autoregressive rule of only looking at the past. The masked convolution solves this by acting as a literal blinder, ensuring the network can only see pixels that have already been generated in the scan order. It is simply a standard convolutional filter that is mathematically multiplied by a binary mask. This mask physically zeroes out any connection, or weight, to pixels that would come after the current pixel in the imposed left-to-right, top-to-bottom scan order. We utilize 2 specific types of masks in the PixelCNN architecture. Type A is used exclusively in the very first layer. Its primary function is the most restrictive. It masks the central pixel itself. Its job is purely to predict the pixel from its predecessors only. Type B is used in all deeper layers of the network. It is slightly less restrictive as it does not mask the central pixel. This allows the network to use the information, or the output, generated in the previous layer to refine its own deep calculations for the current pixel, adding depth while still respecting the sequential order enforced by the preceding Type A mask. The Digital Forger's workshop is built upon a robust architecture designed for efficiency and depth. The overall process flows through 3 key stages. Stage 1 is the initial masked layer. This stage uses a Type A masked convolution, which, as we discussed, masks the center pixel. This layer performs the initial sequential scan of the input image, establishing the very first layer of dependency. Stage 2 is the core of the network, consisting of stacked residual blocks. Each residual block contains several layers, including 1 or more Type B masked convolutions. These blocks are designed for deep processing and feature a crucial architectural enhancement, the skip connection or the feedback loop. In a skip connection, the input to the block is added directly to its output, bypassing the internal layers entirely. This mechanism is vital for 2 reasons. It allows the network to easily pass information through unchanged if the internal block determines that the best strategy is to do nothing, which helps the network learn an identity mapping. More importantly, it prevents signal decay, which is a common problem in very deep networks, effectively combating the informational amnesia that long recurrent structures are susceptible to. This ensures that information from early pixels is retained deep within the network. Stage 3 is the output layers. Once the processing through the residual blocks is complete, final convolutional layers are applied to produce the probability distribution for the value of the next pixel in the sequence, completing the cycle of generation. The result of the digital forger's meticulous deduction is the masterpiece itself. By analyzing the source artifacts, a collection of stylized symbols, the PixelCNN learns the underlying grammar of these objects. It doesn't just memorize the input images, it deduces the unwritten rules of their construction. This includes recognizing line weights, curvature patterns, and common motifs used by the original designer. The model can then generate entirely new creations, unique symbols that adhere perfectly to this learned aesthetic grammar, demonstrating true generative power rather than mere reproduction. The visual quality and coherence of these forgeries are exceptionally high. However, this high fidelity comes with a significant cost: the price of precision. The process is painstakingly, agonizingly slow. Because the model must adhere strictly to the autoregressive principle, every single pixel prediction is sequential and dependent on all previous predictions. To generate a tiny image, say 16 by 16 pixels, the model must perform 256 separate, distinct, and sequential predictions. Unlike a parallel model like a GAN, which can generate the entire image in one pass or step, the PixelCNN cannot. This means that while its generated samples are coherent and high quality, the model is impractical for real-time applications or generating very high-resolution images, illustrating the trade-off inherent in the autoregressive methodology. One significant challenge facing the digital forger involves refining the predicted output, especially for grayscale or color images. The initial problem is this: if we are generating a grayscale image, we are predicting one of 256 possible pixel values. Treating this as a classification task presents a massive difficulty. The model treats two values, say 200 and 201, as completely unrelated, discrete categories, even though they are nearly identical shades of gray. This lack of continuity limits nuance. The solution that refines this craft involves predicting a mixture of simpler distributions instead of predicting a single discrete value. For example, the network might predict the parameters necessary for a combination of 5 individual logistic distributions. The output is no longer a set of 256 discrete probabilities, but a smooth, continuous curve, the final mixture distribution. To generate the actual pixel value, the model first samples which of the subdistributions to utilize, and then samples a specific value from that chosen curve. This powerful technique allows the network to create a rich, continuous output with a significantly reduced number of parameters, compared to classifying all 256 values individually, leading to substantially more nuanced and visually higher quality images. We conclude our investigation into the autoregressive MO by summarizing the key characteristics of our two operatives, the Ghostwriter and the digital forger, and highlighting their shared traits. The Ghostwriter, implemented using the LSTM architecture, operates exclusively in the domain of one-dimensional sequential data, such as text and time series. Its core mechanism relies on recurrent cells equipped with specialized memory protocols, and its key feature is its ability to maintain a complex internal state, or memory, over long periods of time. The digital forger, or PixelCNN, operates in the domain of two-dimensional spatial data, or images. Its mechanism leverages masked convolutions coupled with residual blocks, and its key feature is its ability to impose a necessary sequential order upon a static spatial grid. Despite their differences in domain, they share crucial traits. Their greatest strength is their explicit modeling of the data distribution, which means they calculate the exact probability of every single element. This results in incredibly high-fidelity, coherent samples. However, their defining weakness stems from their inherent sequential nature. Because sampling and generation must happen step by step, the process is extremely slow. Furthermore, despite memory mechanisms, all deep sequential models remain susceptible to long-range memory loss, or amnesia, especially in tasks requiring perfect recall over thousands of steps. Our focused investigation into the mechanics of sequential deduction has now concluded, and we close the file on the Ghostwriter and the digital forger. We have fully documented their methods, recognized their strengths in coherence and high fidelity, and acknowledged the significant limitations imposed by their strictly sequential process. We understand the price of their precision is slowness and a vulnerability to forgetting things that happened long ago. But the findings from this investigation lead us to a chilling realization. These autoregressive models are not acting alone. They are merely highly specialized soldiers within a far larger, more sophisticated generative organization. Our intelligence suggests that there is a mastermind architecture at work, one that observed the limitations of these sequential methods and devised a revolutionary solution. This new system challenges the very rules of sequence and connection that govern the LSTM and the PixelCNN. It figures out how to look at the entire sequence simultaneously, processing all data points in parallel, fundamentally redefining how machines perceive relationships, context, and time. This groundbreaking architecture is the focus of our next briefing. Our next intelligence brief will focus entirely on this new, disruptive force, the transformer architecture. This model is the true mastermind, designed from the ground up to eliminate the inherent sequential bottleneck of LSTMs and PixelCNNs. It achieves this by introducing the revolutionary concept of self-attention, allowing every element in a sequence to instantaneously evaluate its relevance to every other element, regardless of distance. The core mechanics of the transformer revolve around three abstract vectors derived from the input data: the query, the key, and the value. As you see represented here, the interaction between queries and keys determines the attention scores, weighting the importance of every part of the input. These weighted scores are then applied to the values, resulting in an output vector, represented here as V2, that has processed the entire sequence simultaneously. This ability to process data in parallel, ignoring distance and time, is what allows the transformer to handle truly massive datasets and power the largest language models in the world. Get ready to understand how attention is all you need.